Myself is Sai Sudheer, Assistant Professor, EC Department, Srivas Institute of Technology. Today I am giving a short lecture about the discrete time signal processing. So, digital signal processing consists of three words. Coming to the digital, in the olden days, the information always sent by using the analog. Analog signal contains so many drawbacks. That's why we are going to digital. Coming to signal, signal means contains some information. Coming to processing, we have to process the digital signal in so many ways. Okay, representation of discrete time signal, representation of discrete time signal. How we can represent a discrete time signal? Before going to discuss about the discrete time signal, what is meant by continuous signal? Any continuous signal will make it represent like this. Time domain, this is a x of t. It is a continuous time signal. We can sample the continuous time signal. We can convert the continuous time signal into the discrete time signal by sampling. We can sample the continuous time signal with the number of intervals capital N like this. This is a discrete time signal. In continuous time signal, it is a function of t. In discrete time signal, it is a function of n. And coming to the how many ways we can represent a discrete time signal? There are four different ways to represent a discrete time signal. Graphical representation, tabular representation, sequence representation. Last one is functional representation. There are four different ways you can represent any discrete time signal. We can assume we are having a signal x of n at different values of n. At different values of n, x of n equal to at n equal to 0, x of 0, we can assume the value becomes 0. At n equal to 1, x of 1 we can assume as 1. At n equal to 2, x of 2 make it assume as a 2. At n equal to 3, make it assume as a x of 3 value becomes to 1. At n equal to 4, make it assume the x of 4 value becomes 0. Then the graphical representation for this different values of n, x of n is, this is 0, this is 1, this is 2, this is 1, this is 0, 0, 1, 2, 3, 4. It is a graphical representation. In similar way, next notation is tabular representation for different values of n. 0, 1, 2, 3, 4. X of n value becomes 0, 1, 2, 1, 0. It is a tabular representation. Coming to sequence representation, x of n equal to 0, 1, 2, 3, 4. This is the way we have to indicate the sequence representation. The arrow indicates at n equal to 0, It is a sequence representation. Next, functional representation. X of n equal to 0 at n equal to 0, 1 at n equal to 1, 2 at n equal to 2, 1 at n equal to 3, 0 at n equal to 4. This is a functional representation. In these four different ways, we can represent any discrete time signal. Coming to the next, elementary discrete time signals. Elementary discrete time signals. What are the different elementary discrete time signals? First one is unit step sequence. Second one is unit impulse sequence. Third one is unit ramp sequence. Fourth one is unit parabolic sequence. Fifth one is sinusoidal sequence. Sixth one is real exponential sequence. And seventh one is complex exponential sequence. These are different elementary discrete time signals. Coming to the first sequence, unit step sequence. Unit step sequence can occur from 0 to infinity, represented as u of n, and the value becomes 1. From 0 to plus infinity, and the value becomes 0 less than 0. That is u of n equal to 1 for n greater than or equal to 0, 0 for n less than 0. And second one is unit impulse sequence, can be represented by del of n. Del of n can exist only at n equal to 0. Only at n equal to 0. The value becomes 1. Other than n equal to 0, the value becomes 0. Del of n equal to 1 for n equal to 0. This value becomes 0 for n not equal to 0. Coming to the third one, unit ramp sequence. Make it represented by like this: r of n, discrete time variable is n. This is the way we have to represent the unit ramp signal for different values of n. 1, 2, 3, 4, 5, 6 and so on. Function is r of n equal to n for n greater than or equal to 0. 0 for n less than 0. For different values of n less than 0, r of n becomes 0. And fourth one is unit parabolic sequence, p of n. 0 and 1, 2, 3, 4, 5. The function is p of n equal to n square by 2 for n greater than or equal to 0, 0 for n less than 0. Value becomes at 1 equal at 1 0.5, at 2 1, at 3, at n equal to 3, 3 square by 2 4.5, at n equal to 4, 4 square by 2 8, at n equal to 5, 5 square by 2, the value becomes 12.5. Similarly, up to n equal to infinity, n less than 0, value becomes 0. It is the p of n. And the last three signals are sinusoidal signal. This is the way we have to represent sinusoidal signal in discrete time signals. Okay, x of t equal to a sin omega naught t n 0. Okay, and the remaining two are real exponential sequences. X of n equal to a e power minus at n. So this is the x of n equal to a e power minus is the real exponential sequence for small a greater than 1, and the last one is complex exponential sequence, and this is the way complex exponential sequence in continuous time domain. If you can make it sample for different values of capital N, the same figure can make it represent in a complex exponential sequence. Thank you.